Welcome to homework.
In this problem, we are given these two half reactions that occur within a galvanic cell. In part A, we want to write out what the overall cell reaction is, as well as the cell potential. We know that for galvanic cells, the cell potential has to be positive. So therefore, the half reaction with the larger standard reduction potential will be the half reaction that undergoes reduction, while the other one will be the one that undergoes oxidation. So based on the differences in the standard reduction potentials, we know that the second half reaction will have to be reversed since it is smaller and therefore will undergo oxidation. So the top half reaction will undergo reduction. So that's Au 3 plus 3 electrons goes to solid gold. And the standard reduction potential for that was 1.50 volts. And now the second half reaction will be flipped to undergo oxidation. So we have TL going to TL plus 1 electron. And now we flip the sign of the standard reduction potential since this half reaction has been reversed to undergo oxidation. So instead of negative 0.34, it's positive 0.34. So now we combine these two together to get the overall reaction as well as the standard cell potential. We have to multiply the second reaction by 3 so that we have 3 electrons on each side to cancel out. And so the overall cell reaction we are left with is Au 3 plus aqueous plus 3 solid thallium goes to Au solid plus 3 TL plus aqueous. And the standard cell potential is then just equal to 1.50 plus 0.34. And that comes out to 1.84 volts. And now in part B, we want to calculate the value of the change in Gibbs free energy at standard conditions, delta G, which is equal to negative NFE. And so that's equal to negative N is the number of moles of electrons. We see that we had 3 electrons canceling out. So that's 3 moles of electrons times Faraday's constant, 96,485 coulombs per mole of electrons, times the standard cell potential, which we just calculated to be 1.84 volts or joules per coulomb. And now when we calculate out delta G, we are left with energy units of joules. And if we divide by 1,000, we can get delta G in units of kilojoules to come out to about negative 533 kilojoules. And now we also want to find the value of K, the equilibrium constant. We know that when a galvanic cell is at equilibrium, the cell potential is equal to 0. So from the Nernst equation, we can say that 0 is equal to the cell potential at standard conditions, which was, again, 1.84 volts minus 0.0591 divided by N, which, again, is 3 electrons, 3 moles of electrons. And then we do the log of Q, but since the cell potential is 0, this corresponds to the equilibrium constant K. So we can rearrange that equation now to solve for K. And when we do, we should get K is equal to about 2.5 times 10 to the power of 93. And now in part C, we are given non-standard concentrations for both TL plus and AU3 plus, and we want to determine the cell potential. So we again use a Nernst equation, and we need to calculate Q. We know that from the reaction, this is equal to TL plus ions cubed divided by the AU plus ions concentration, AU from this reaction AU3 plus ions. And we are given the molar concentrations for each one of those in part C. And so that is 1.0 times 10 to the negative fourth molar cubed divided by 1.0 times 10 to the negative 2 molar for AU3 plus. And so when we plug in that value of Q into the Nernst equation, we have the non-standard cell potential equals the standard cell potential, again 1.884 volts, minus 0.0591 divided by N, moles of electrons again is 3, and then we multiply that by the log of Q. And again, we calculated Q based on this ratio. And so when we solve that all out for the cell potential, we should get a final answer of about 2.04 volts.